Hello students. So I'm back here with a new video. Hope you are understanding my videos and following my videos. Please, if you have any doubts, you can ask me in the comments and let me solve your problems. And also it will be a pleasure of mine to solve your problems and come to your rescue when you have some doubts regarding the subject. It may be any chapter. Okay, first the 11th and 12th, both the chapters, any chapters you can ask the doubts in physics. Okay, because I am your, as you know, I'm your physics wali madam. So like, share, subscribe to my channel, and let's begin. So in the previous video we had discussed about the significant figures. So now I'm going to tell you the rules followed to write the significant figures. Okay, so let us begin with, I will write the heading. Take your notebook and pen. Don't miss any point. Rules to write significant digits. Okay, so let us see the first one. All the non-zero digits are significant. So first of all the non-zero digits, the rule is all the non-zero numbers are significant. Okay. The second one, all the zeros between the two non-zero digits are significant, irrespective of the decimal point. All the zeros between two non-zero numbers are significant. Irrespective of the decimal point. Okay, so for example, 23.01. So 0 is in between the non-zero numbers. So here the significant figures will be 4 significant figures, or you can also write it as significant digits. Okay, then the third rule, if the number is less than 1, the zeros to the right of the decimal point and to the left of the first non-zero digit are not significant. If the number is less than 1, the zeros to the right of the decimal point, right of the decimal point, but to the left of the first non-zero digit are not significant. Okay, so these are three rules. We have two more rules. Fourth rule is the zeros at the end end of a number without decimal point decimal point I will do it like this because I can't write properly without the decimal point are not significant. Fifth one is the zeros at the end of a number with a decimal point are significant. The zeros at the end of a number with a decimal point are significant. So example I will give you. So here the fourth one, the zeros at the end of a number without decimal point. Suppose it is 2400. So here there is no decimal point. Okay. So here the significant figure is 2. And how many ever it may be, 2000 or 2400, 24,000 or 2,40,000, anyhow how much the big number it is, but if there are zeros without a decimal point, then it will be only two significant figure. Then if we place for the fifth point example, let us see. Now if I place a point here, okay, so if I place a point here and write the so here if I place a point here and write here 0 0, then there will be 1 2 3 4 5 6 7 8 significant figures. Okay, So this is a magic and this is the trick of the significant figures. So this is the fourth point, answer to the fourth point, and this is the answer to the fifth point. So suppose one more example I will give you. 1000.00. So here how many digits, significant figures? There are 6 significant figures. Okay, I hope you understood. So let us proceed to the next, that is we will see the important topic of this uh, lesson chapter, that is the units and the measurement. So before going to the dimensions, let us see the rounding of the significant figures, rounding off and writing the significant figure. Suppose if it is 12.45 and if it is asked to round off to three significant figures. Now we have the original number, we have 4 significant figures. Okay, but the question is round off to 3 and write the significant figure. So here, as there is a 5 here, we can carry 1 to the third digit, that is 4, and we can omit the 5 number, that is we can write this as 12.5, and now we can write it as 3 significant figure. Okay, so suppose if it was 12.43 and round off to 3 significant figures. So originally it is 4 significant figure. Then we can omit this one because it is less than 5. So we can just write it as 12.4. So we have now 3 significant figures. Okay, another example I will give you. So suppose it is 236.74. So here how many significant figures are there? There are 5 significant figures. Okay, now the question is asked like find the round off to 4 significant figures or 3 significant. Let us find out for 4 significant figures. So as 4 is the least one, it is lesser than 5, so we can omit this one 4 and we can get to up to 4 significant figure, that is 236.7. So it will be 4 significant figure. Now if it is asked for 3 significant figure, we can, as 7 we'll omit this 4 and we can take 7, that is it is greater than 5. We can carry 1 to the 6 and now we can write it as 237, and here it is 3 significant figure. So this is how we can round off and write the significant figures. So let us go to the next topic of this chapter, that is dimensions. So dimensions. So dimensions are nothing but, as we have done the base quantities, base units, so that units we have to write within the bracket. Some we will use the units and some we will give the notations of uh, the physical quantities itself. So for example, length. So length, directly we will take the dimensions of length as, with always it is written in a square bracket, capital L. Okay, and mass, M, capital M. We will not take here kg or meter. We will avoid that and we'll just take the first letter of the physical quantity, that is L and M. So don't confuse here. So this is the rule. This is how we should take it. Then time, capital T within the square bracket. Then current, electric current, will not take here I, we will, or C. We are going to take the unit, capital A, because already it is capital A. We'll take the capital A. Then temperature, it is taken as Kelvin, capital K. Okay. Then luminous intensity, we will take it as CD, because we cannot take L because already we have taken for length L. That's why we'll take it as CD. Then the amount of substance, mole within the square bracket, MOL. Okay. So these are the dimensions we use in the units and measurement chapter. Capital L for length, capital M for mass, time for time, capital T, then current, capital A, temperature K, capital K, then luminous intensity CD, then amount of substance mole. Okay. So here this is how we have to write the dimensions. So let us start the dimensions. So for example, now force. I want to write the dimension for force. So force formula is m into A, that is m is for mass and A is the acceleration due to gravity. So m, capital M will write m, and A is meter per second. So meter is length and second square, that is T raised to minus 2. So like this we are going to write the force. Now let us see for velocity. That is displacement by time. So here there is no mass. If there is no mass, we will write it as m naught, or simply you can omit it. But if it is asked all the three, then write m naught, L, T raised to minus 1. L is for the displacement, that is measured in meter only. Then time is per time. Okay. Okay. Next we will see the work. Sorry. For work, it is force into displacement. So already we got the force here and displacement is length. So first I will write the force, ml t raised to minus 2 into displacement is L. So we'll combine these two now. So L raised to 1, here is L raised to 1. So it will be 1 plus 1 is 2. So it is m L square t raised to minus 2. Okay. Next we'll write angular momentum. So that is L is equal to P into R. So P is what? It is m into V into R. So m is capital M. For velocity is L t raised to minus 1 into again L. So this is ml square t raised to minus 1. Right? Okay. Now let us see the kinetic energy. Half mv square. So half we will not consider because it is a constant. So dimensions cannot be taken for constants and the trigonometric functions. So here m is capital M and v square is, that is the velocity, that is L square t raised to minus 2. So like this you have to write the dimensions of a physical quantity. I hope you have understood. So let us go to the other section. So now let us know what is the difference between a dimensional formula and a dimensional equation. So here dimensional formula. Okay, dimensional formula is expressing a physical quantity in terms of dimensions only. So if velocity asked, then we can take directly the, don't take the equivalent value, equal value is equal to, you should not take, just you write the dimensional formula m naught L t raised to minus 1. So this is the dimensional formula. And dimensional equation is, I will show you. So there should be a LHS and RHS in the equation. So velocity is equal to m naught L t raised to minus 1. So this is the equation. So here, so I hope you have understood what is the difference between a dimensional formula and the dimensional equation. Formula is just, you have to write the equation, formula of the velocity, then remove the dimensions of it, and equation is you have to write the LHS as well as the RHS. So now we'll see the dimensional analysis. It is also called the dimensional analysis and its application. So heading will write dimension analysis and its application. So here, first of all, the first one is convert the unit of a physical quantity from one system to another. So it is convert a physical quantity, unit of a physical quantity physical quantity from one system to another. Okay, so this is like, so let us see. So let us see how to convert the system from one form to another. So let us take force example. So in SI system, force is taken in terms of Newton and CGS as dyne. So we'll take the values, the dimensions here as M2, M1, M1, L1, T1, T is same, and for dyne we will take it as M2, L2, T. Okay, so here one dyne, one Newton upon one dyne you have to write, that is equal to, so the force equation is ml t raised to minus 2, so m2 l2 t raised to minus 2 upon m1 l1 t raised to minus 2. So m2, this both will get cancelled, so because they are same, m2 by m1, let us take in one single bracket, and this as l2 upon l1. Okay, so here mass is in 1 kilogram upon 1 gram into 1 meter upon 1 centimeter. So now here this kilogram and meter will take in CGS only. So this is 1000 gram upon 1 gram into 100. So 1 meter is 100 centimeter. 100 centimeter by 1 centimeter. So units will cancel out. So it is 10 to the power of 3 into 10 to the power of 2. So it will be 10 to the power of 5. So 1 Newton is equal to, so this denominator will take here 10 to the power of 5 dyne. So this is how we have to write conversion of the unit from one form to another form. So we have converted here from the SI system to CGS system. Hope you have understood this. Let us go to the second application, that is checking the correction of the equation. Correctness of the equation. So here let us take one equation, v is equal to u plus at, simple equation. I will take the mechanical equation. So each one of the each one of the physical quantity we have to solve. V is equal to, the dimensions we have to take, v is l t raised to minus 1, so we got v value. Then u is what, it is the initial velocity, so it will be same, l t raised to minus 1. Then at, a into t, so a is what, l t raised to minus 2 into t. So again it will be l t raised to minus 2 and plus 1, it is minus 1. So all are equal, hence the equation is dimensionally correct. So we have to solve in this form. One other example I will give for correctness. So let us take s is equal to ut plus half at square. So the constant values we cannot take the dimension. So let us take first s is L, ut is L t raised to minus 1 into t. So it will be L only. Then at square is equal to L t raised to minus 2 into t square. Again it will be L. So all are equal. L, we got all the equal dimensions. So therefore it is dimensionally correct. So this is how we have to check the correctness of the equation. So next third one, let us see. Deriving a correct relation. Third application it is deriving a correct relation between the different physical quantities. Between the different physical quantities. So let us take the example of a simple pendulum where we'll take the time period of the oscillation of the simple pendulum, which is proportional to the mass. Let us take the power as x, then length raised to y and g raised to z. So we have to derive the relations between these. So let us take the t as k m raised to x, l raised to y, g raised to z. So here let us take t as the dimension of time as m naught, l naught, t raised to 1. So for time being we'll not consider k value. Afterwards we can insert it. So m is the mass. So it is m raised to x, l is length, l raised to y, and g is acceleration due to gravity. So acceleration dimension we will take it as l t raised to minus 2 raised to z. So this is x value will equate the powers here. So m raised to x, so none of them having in the RHS we don't have any m value. So x is equated to the LHS, that is m raised to 0. X is equal to 0. Then length you can see here l raised to y and l raised to z. So we'll take the powers only. Y plus z is equal to here l is equal to 0. Okay, then time here it is minus 2z is equal to here time is 1. So first of all we will take the z value, we'll find the z value. Z is equal to minus 1 upon 2. So now x we got and z we got. We can substitute here in this equation. Y minus half equal to 0. So y is equal to half. So experimentally k value is 2 pi because oscillation, for complete oscillation in the simple pendulum it will make 2 pi oscillation, that is full completely if we take it will be 2 pi. So it is 2 pi. So therefore t is equal to 2 pi So L value was, so M is 0, M will not take M. So L value is L raised to Y because it is half. So we'll take under root by L upon Z value, we got it as minus half. So that is G is G raised to minus half. So it will be in the denominator but under the root. So the time period for a simple pendulum is, we have got the equation as T equal to 2 pi under root of L upon G. Hope you have understood the topic. So this comes to the end of the units and measurement chapter. Then in the next session, we will take the motion in straight line chapter. Thank you. Bye bye.